And we've been talking about these one-dimensional quantum mechanics problems that are governed, let's use that word, by Schrodinger's wave equation. The first one we did was an infinite square well. I think a lot of people like that because it looks a whole lot like a classical problem of a standing wave on a string that at the time acousticians and physicists at the turn of the century and into the early part of the 1900s, they knew the solution to it. And so they constructed this one-dimensional well that was squared off at the bottom that had potential boundaries that were infinitely tall, and the math was easy. It isn't necessarily a reality problem, something that could be modeling something else that they could build in the laboratory, but it gave them insight into quantum mechanics because it predicted discrete states, which we called wave functions. And the purpose of wave functions is to square them, multiply them by their complex conjugate to get a probability density that could predict what the probability that a particle will be in some region of space, delta x or dx if it's a small region. It also gave them the ability to calculate expectation values, average values of properties that they could observe in the laboratory for the particle that was trapped in this well. And that would be position probability, a position expectation value, then an average position, momentum, and energy. And in order to unlock that information, we introduce these things called operators. Okay. And they're just functions that act on the wave function and unmask what the momentum is if you use the right operator, IH bar times the derivative with respect to x, and energy. The operator is minus IH bar derivative with respect to time. Go figure. Okay, and so that information is pulled out. One other thing about the wave functions we found, they were discrete. Okay, they had particular values, particular shapes. We called them stationary states. Maybe it looks like a standing wave on a string. That was a great analogy there. But each one had a different energy associated with it in one dimension. Okay, so now we modified that a little bit. We shortened up the infinite boundaries, and we did what's called a finite square well problem. And that's all well and good. What we found though was a little bit bizarre, that's probably the best word I got for it, is unlike the infinite square well where the particle cannot get past the boundaries of the well, in the finite square well, there is a probability that the particle will be outside the boundaries of the well, even if the particle doesn't have sufficient energy to escape from the well. That is total energy greater than the potential energy height of the well. And yet sometimes there is a probability, very small probability in most cases, but a probability that a particle trapped in a finite well can be outside of that well. Interesting thought, because classically there is no explanation for that. If you don't have enough energy to get out of a well with a finite boundary, if your total energy doesn't exceed the energy of the boundary height that is keeping you inside, well, it would require negative kinetic energy in order to get out, and that doesn't exist. Kinetic energy is positive definite because it's got things that are squared. You either square momentum or you square velocity, and so it's always a positive number. But yet quantum mechanics predicts the particle could be outside the boundaries of the well as if it somehow had some sort of negative kinetic energy. Don't know that we understand it. A lot of people argued over this in the early part of the 1900s, but it exists. The next problem that we started talking about on Wednesday, I guess, was the barrier. And I've got some math, unfortunately, to show you on that. Um, and so everybody loves math. Let's share with you my iPad. And hopefully I can screen mirror here. There it is. And yep, you're seeing it. That looks good. And so we talked, instead of a well, just flip the well upside down and it becomes a barrier with some height in potential V0. And remember, V0 is not volts, It's energy. Why we're not using U is a darn good question, which I used to ask when I was an undergraduate. I don't have an answer. We just decide that potential energy in joules or in EV is given the symbol V now. And what we're looking at here is a particle whose total energy E, sum of potential and kinetic energy. We're going to assume these particles are not moving at relativistic speed. So I don't think we're going to spend much time worrying about rest mass. I'm looking at any of the problems today to see if that's necessary. And I'm looking at 5 MeV and their alpha particles. And so I don't think we need to include rest mass in relativistic speeds. And I think that'll be true for most problems we do. If you ever have a very high energy particle, well, by all means, start throwing in the relativistic calculations. But I think we can stick with fairly classical explanations here with respect to speed, not with respect to the fact that it's quantum mechanics. So in any event, there's our particle with some total energy greater than the potential energy. And the particle is moving along in the positive x direction. The odd thing here is that in quantum mechanics, the wave function, or at least some of the wave function, gets reflected back. It's as if you were flying an airplane well over the top of a mountain, gravitational potential energy wise anyway, and somehow there's a probability that the airplane reflects backwards, bounces backwards off a mountain that's way below it. And of course, there's no classical explanation for it. We expect 100% transmission of a classical particle moving over a potential barrier when its energy is greater than that of the potential barrier, but not so in quantum mechanics. You always have this thing right here to bug us. Okay, and there's some statements here about what the wave number is for the wave functions in each of the regions. I'll show you where those come from in just a second here. Okay, so that's the problem we were thinking about. I always got to remember to go to the hand thing before I try to scroll up. And my thought on Wednesday for you was, hey, this could be like light hitting us like a microscope slide, a thin piece of glass. Some of it transmits through, some of it's reflected. That makes sense for an electromagnetic radiation for light, which when it's a wave. But we're saying that's happening with particles too, very small particles. Okay, and so you can see the regions of the barrier that we're kind of modeling here in a one-dimensional case: 1, 2, and 3, air, glass, air, perhaps, or just medium 1, medium 2, medium 3 in quantum mechanics. And so I got to do some math for you now, because I think I said that these one-dimensional problems are bounded by Schrodinger's wave equation and into 3 regions. And just so you don't forget what the regions are, there's 1, there's 2, and there's 3. Region 1, region 2, and region 3. Those are Schrodinger's wave equations. And I say the corresponding solutions are in that middle section there. They're complex exponentials, and I'll show that here in just a second. But I think if you consider a particle just moving to the right this way, we can simplify these solutions. And in fact, we're going to completely ignore what's going on in the middle section. So let me I got to go to the finger thing to move. Trying to move while I'm still in a pen mode, I'll never get it. Let's go through Schrodinger's wave equation and see where those things I just wrote came from. And I'm going to use this notation because I realize my penmanship is better if I do that. Minus h bar squared over 2m. And instead of writing the second derivative as a ratio, I'm going to go with the two slashes up there, and that means a second derivative. And I'm hoping you've seen that notation multiple times. In fact, that may be what the calculus people prefer. Plus the potential energy, which in this case is that barrier height, potential energy 0. So I'm looking at region 2 here right now. Okay, so this is the wave function in region 2 times the wave function in region 2 is equal to the total energy of the particle times the wave function in medium 2, right? Which, if you're looking at the optics analogy, that's the glass section, the thing in the middle. All right, well, let's see. Just solve this thing a little bit. Manipulate it is generally how you solve it. And the first thing I'm going to do, that's a second derivative, region 2. I'm going to move this thing to the other side of the equation and potential to the other side of the equation. And so I have the total energy minus the potential energy. That's nothing more than the kinetic energy, right? Times the wave function, which I'll factor out. I guess the next step is to, I don't need the heading to, I don't need the top and the bottom. It's lowercase psi I'm working with here. Psi 2, second derivative, is equal to then 2m over h bar squared. Don't forget the negative sign times the kinetic energy E minus V0 times the wave function. Okay, and the simplification is to call this thing right here k squared. So this is equal to minus k squared. And of course, it's k squared in region 2 times the wave function in region 2. And so that's why we said on the first slide that the wave number in region 2 is equal to the square root of 2m over h bar squared. Some people bring that h bar squared outside of the radical. It's up to you. That's style. And then times the kinetic energy, the total energy minus the potential energy. Okay. And if you recall, that's what we maintained right here. Right. So I think I've shown that. And so now the question is, what's the solution to that? Well, I'm not the differential equations teacher. Hopefully you'll get to do that next semester. This is irritating me that I did that, so I got to get rid of that little line. What is the solution to that differential equation? And the answer, I think, is a guess. Okay, that's how we're taught in differential equations to solve this particular equation. My guess is going to be that psi 2 is some constant, and I don't know what constant to use. I'm going to use A, B, C, D, F, and G in a second. So I'm going to use E right now just to show what the solution to this differential equation is, that the second derivative of psi with respect to x is equal to minus this grouping of constants, k2 squared times the wave function, okay? And I'm going to make my guess that it's this. And I went first with I times that k2 times x. And that's a 2 that just supposed to be a Roman numeral 2, but it didn't look really good. Okay, there it is. That's my solution. How do I know? Okay, well, the answer is like solving a quadratic when you're in like the 6th or 7th grade. Somebody said solve the quadratic, you guessed at a number, you plugged it into the equation, you saw if it worked. If it did, it's a solution. It may not be the only solution now. Somebody told you eventually that for quadratics, there's going to be 2 solutions. And so you can keep guessing and checking. And that's what we wind up doing here. And we have the same problem. Once you get a solution that works, like this one, which I'm going to show you it works, is it the only one? Is there another solution that could exist? And that is some of the mathematical theory that you'll learn in differential equations next semester. Well, the point, I guess, is if it works, I better take some derivatives. And the good news about this particular guess is the chain rule makes taking a derivative with respect to x the same as just multiplying by that thing right there, right? Times e exponential I k2 x. And then, of course, the next derivative, the second derivative, well, that would just bring down another ik. So that makes it minus k squared, e to the e, the constant, times e to the ik2x, which if you look is just minus k squared times my guess. So I've done it, right? QED, that's proven. That is a solution, okay? So look, it looks, I've recovered the differential equation right back by substituting in, right? I've got exactly that right here and here. And I don't know why I wrote 3. Don't ask me. That's just a 2, right? We're still in region 2, like we said. All right, so I've shown this is the thing that I put a square box around is a solution. Here's the problem. Is it the only solution? The answer is no, because what if I put a negative sign right there? When I take the derivative, that would put a negative sign right there. And then when I bring down a second minus ik, I'm still going to get minus k squared. So this still gets the same answer. And in addition to the first solution I showed you, having a negative sign up in the exponent is also a solution. And so the mathematicians got together and they say, well, if one of them is a solution and the other one's a solution, linear combinations of those solutions are also solutions. And that's a math theory that you can kind of take to the bank. And so we're going to say that the solution here in medium two is just equal to, let's see, the way I'll stay with our textbooks ordering, a constant, changed from E now to C because we're going to have a bunch of different constants because we got three regions. And with C is the positive solution. And then another constant, again, I can't use E because that was my demonstration constant, E to the minus K2X. And so that is the solution in the middle region, okay? So we're partway there. Let's go back and look at the other two regions, region 1 and 3. And what I think I've just recovered is this, okay? So let's look at regions 1 and 3. What's different in region 1 and 3? Well, in region 1 and 3, the potential is equal to 0. Potential is equal to 0. And so that means this term right here doesn't exist in the shorter wave equation and come about it exactly the same way. But it will still have solutions that are exponentials. The difference, though, is that K in region 1 will just be the square root of 2m over h bar squared times the total energy, because there is no potential energy in region 1. And I think region 3 will have exactly the same form. Okay, and so I've got now three equations for wave functions. Again, I'm going to have a e to the plus I, whatever the k is, k1 or k3 times x, and e to the minus I times k1 or k3 times x. Okay, exactly as written right here and right here. Differential equations 101, make a guess, plug it in, see if it works. If it works, it's a solution. Take a second to think about, are there any other solutions that might work? In this case, there is. And by the way, you might even think about, how about sines, cosines, look at all the hyperbolic sines, hyperbolic cosines, will they work? E to the, just a constant without the complex I up in the exponent times x, would that work? You think about all those possible functions that might solve the equation. Sines and cosines might have worked here too, but we went with complex exponentials just because it's easier to do. And we see that there's two variants, one with e to the plus ikx, one with e to the minus ikx. And the math theory says that if either of those is a solution, then the linear combination of them is also the solution. All right, now we're going to ignore the middle for just a second, and you'll see why. We'll bring it back later, but we're really interested in that particle moving to the right, and then go back to my original color, what gets reflected back and what gets transmitted through. Okay, that's all we're really interested in. And it seems to me that I've only written lowercase psi. Uppercase psi, remember, that I tried to write one time, is lowercase psi times e to the minus I omega t. And so these solutions, like that part right there, okay, really is a e to the plus I k x, e to the minus I k x. And I guess that is a particle, well, it's a traveling wave when the wave is going to the right. Remember, back even in PHY211, we said if a wave has an argument that looks like that, where there's an opposite sign between the thing in front of the kx term and the thing in front of the omega t term, we said that thing was going to the right. Whereas if they have the same sign, sine of kx plus omega t, that's something going to the left. Well, they could both be negative and also going to the left. It could be minus kx minus omega t. That would still be going to the left. And so the way we interpret these two solutions in region 1 is the one with the positive exponent, because the omega would be negative. That one's moving this way. And the one with the negative is moving the other direction. And same thing out here in region 3. As I said, we're going to ignore region 2 for just a bit. The one with the coefficient f and the positive ik exponent is going to the right, and then this one with the g e to the minus kx, it's going to the left. And notice what I did there. Since 1 and 3 are the same, we're just going to substitute and use 1 all the way through. All right, well, that helps us out a little bit, I guess, because I think we can label then this term, the A1, the one that I got circled, that's the thing moving to the right. That's my incident particle being represented by a wave that's traveling. Okay, the one with the B here, this guy right here, that's the wave that's being reflected. We're ignoring the middle, we're ignoring 2 then. This guy over here, that's the one that's the F e to the ik1x. And I can throw out G, right? The reason is G doesn't have any barrier to reflect back off of. Okay, so that it would be physically impossible actually, that a wave will be coming back unless there's some kind of barrier further on down the line as you move in the x direction. So we can just kind of ignore that. It doesn't exist. And these are the 3 waves that we care about that are representing the particle. Wave coming in, wave reflecting back, and then the wave that ultimately gets transmitted beyond the barrier, because it can. It's a classical wave. The hard part for me is, why is there that reflected back piece? All right, well, here's what we're going to do. We're going to define some things. Okay, we're going to define a reflection and a transmission coefficient, which are probabilities of reflection and probabilities of transmission. And so since the wave function squared multiplied by its own complex conjugate is a probability density, hopefully it makes sense that since we had 3 waves, I'll write them again, a e to the I k1x, b e to the minus I k1x, that was the wave that was moving to the right, coming in, the incident wave. That's the one that's reflected off the barrier, moving to the left. Okay, and then the third one was f e to the I k1. It's actually in region 3 though, but we're calling it 1 times x. That's the one that gets transmitted through. Okay, well, hopefully it makes sense that the reflection probability is b star b over a star a. What happened to the exponential? Remember, when I multiply by its complex conjugate, this term gets multiplied by e to the minus I k1x, and it just goes to 1. And so all I'm left with is a star a. And it presumes that a and b and f here could be complex. Very often they'll be real numbers when we're doing it, but they could actually be complex numbers in the most general problem. And the transmission coefficient, well, that would be just f star f over what comes in. So it's almost like I don't want to say an efficiency. Yeah, it could be seen as an efficiency. You put in a star a, that's the incident particle. What do you get out when you're reflecting? B star b. And what do you get out when you're transmitting? F star f, f complex conjugate times f. Okay, so that's how we're going to define these constants. Now, I got some more math to do, because we're going to show that the transmission coefficient is this. Remember, though, you really only have to get one or the other. You don't have to get both reflection and transmission. If you have either one of them, hopefully it makes sense that the probability of reflection plus the probability of transmission has to add up to be 1. Otherwise, the particle disintegrates, and we're not allowing for that possibility. We're not allowing for the possibility that the particle just disappears. We're not allowing for a possibility that another particle shows up. The particle that comes in, being represented by a wave, is either reflected or transmitted past this barrier, one or the other. And so those 2 probabilities have to add up to be equal to 1. All right, says something about boundary conditions here, right? And so, so let's play that boundary condition game using those equations right here. Oh, come on. I have to erase because I tried to move without going to the finger thing. And I'll rewrite what our waves are. And I'm going to now start including that middle thing that I neglected. And so let's go back to the wave functions. No, 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 not that guy. That guy. And I don't need the foot, lowercase psi. And this is in region 1. And we say that that's a wave going to the right, A, E to the I, K, 1, X, plus a reflected wave going to the left. That's it. Let's recover what I said about that middle region, 2, where the barrier is. That's going to be C, E to the I, K2, X, plus D, E to the minus I, K2, X. And I see I didn't put a 1 right there. Hopefully you knew it was 1. And then lastly, in the third region, let's see, we skipped E. That's why I used it before. In the third region, we just have F, E to the I. It's K3, but K3 we showed is exactly the same as K1. So I could just write K1 right there, times X. And remember, we don't have that G coming back because there's no wave, nothing to reflect the particle once it gets beyond the barrier. So it can only be moving to the right. And that's why that's missing right here. All right, here's the next thing you'll be doing a lot of in differential equations next year, something called boundary conditions. And remember, we said these wave functions have to meet a couple criteria. We said that at the boundary, the wave functions have to be the same. And so we're saying that these two guys have to be the same at x equal to 0 and at x equal to L. And we're saying that these two guys have to be the same at x equal to 0 and x equal to L. We also said that the wave function must be normalizable. So out at infinity, we've got some trouble out there, but we'll just stay with x equal to 0 and x equal to L. But the other thing we said, the third thing, was that the derivative of the wave functions must be continuous at the boundary. We said that, say, at the first part of the boundary right here, you can't have one wave function doing this and then the next wave function doing something like that. That would be even though the wave function itself is continuous, the derivative is discontinuous, not allowed. Okay, and so those are our boundary conditions. So let's look at them one at a time. And we won't worry too much about the infinity thing, other than the fact that that's why we threw out this term that would have been a G right here, okay, because there's nothing out to reflect back between here and infinity. But the first one is that at x equal to 0, psi 1, the wave function in region 1, has to be equal to 2. And if you look at it, I think, plug in 0 for x in every place, I think you come to the conclusion that A plus B has to be equal to C plus D. Good to go? That one's pretty straightforward. I like that one. Okay, the harder one, of course, is that in addition to the wave function being continuous, I try to just fit that in right there. At x equal to 0, the first derivative also has to be the same. And I don't know why I wrote 2 there. I've been using Roman numerals to be consistent. Okay, and so I better take those derivatives first. Let's see, brings down an ik and a minus ik, right? Because I'm just barely not going to be able to see that thing. So I think it's ik1 times a e to the positive I k1x. And then let's take the derivative of b. That's not, I'm going to bring down a minus thing. So why don't I, minus ik, so why don't I make that minus ik1, and then it's b times e to the minus ik1x. Okay, that's the derivative of the wave function in region 1, has to be equal to, let's see, it'd be ik2 e to the ik2 x. And then I think it's also going to be minus here, minus ik2 e to the minus ik2 x. And that's a little hard to read right there, so let's fix that. ik2 x. And those things have to be equal at x equal to 0. Well, x equal to 0 makes that go away, because that's just 1, that's just 1, that's just 1, that's just 1. And so I think I could cancel those i's too, can't I? The I cancels, the I cancels, the I cancels, the I cancels. I think this tells me that K1, which remember was 2m times the total energy over h bar squared, take the square root of all that. Okay, K1 times the difference, just a bunch of constants, times the difference in A and B, right? Difference because of that is equal to K2 times the difference. Oh, no, I forgot to write some things here, didn't I? Like I didn't bring the constant C right there, and I didn't bring the constant D right there. C minus D, the two constants would have to still come down. Yeah, I did the chain rule part. I brought down the I K2, but I didn't write the constant when I was taking the derivatives. So I got two equations here, but I got four unknowns, A, B, C, and D, don't I? So that's problematic. I can't solve two equations to get four unknowns. So I better go look at another location. X equal to L. Same thing has to be true, right? Psi 1. Well, no, psi 1 isn't at x equal to L. Psi 2 and psi 3 meet up at x equal to L. So those guys have to be equal. And let's see, that tells me, I think, C e to the I K2, and I remember the coefficient this time, that's good, times L plus D e to the I K2 times L has to be equal to wave function in region 3, F e to the I K3 L. Nothing I can do to simplify that, I don't think. But now I have a third equation. Oh, darn it, I brought in a fifth unknown though, didn't I? Now I got F as well that I don't know. So, but I'm making progress, I think. I got three equations and five unknowns now, A, B, C, and D, the coefficients that matter, because they matter. Just take a break from doing great calculus we need what is B, what is A, what is F, what is A in order to find these reflection coefficients. At the very least, we need to know F, don't we? If we knew F in terms of A, well, then we could get a transmission coefficient. So it's not necessary to get all the coefficients. C and D are kind of irrelevant for transmission or reflection coefficients. But if I could get F in terms of A, well, then I can solve for what the transmission coefficient is, the probability of transmitting by this barrier. All right, well, the last thing you probably guessed I have to do is I have to look at the derivative of wave function 2, and it has to be equal to the derivative of wave function 3 at the boundary. All right, so let's see if I can take that derivative without dropping a coefficient like I did last time. Okay, the derivative of psi 2 is going to be I K2 C e to the I K2 x. I'm not going to write a plus sign there because I'm going to bring down a minus IK, aren't I? I see an issue. Now that I look at it, look right here. Isn't there a negative sign right there? Yeah, keep me honest on things like that. Okay, I've got to get the signs right. Otherwise, everything will not come out to the answer I need. Okay, so let's see. Minus IK 2, region 2, times d e to the minus ik2 times x. Okay, all of that has to be equal to the derivative on the other side. Okay, pen just turned off. There we go. IK3 F e to the IK3 X. And those are the derivatives. And I'm going to insert an L in place of X right there, there, and there. And what can I cancel? I think I can cancel the I's at least. The I's cancel. And I think I'm left with K2 times C times e to the IK2L minus K2D e to the minus IK2L has to be equal to K3 F e to the IK3 times L. I think that's my fourth equation. See if I got it right. I could certainly factor out the K2 if I wanted to simplify this a little more, but now I've got four equations, 5 unknowns. I don't need to solve for all 5 unknowns, but I do need to figure out what the coefficient F is, eliminating C and D and B to figure out what is F in terms of the coefficient A. If mathematically I can do that, I can arrive at a transmission coefficient. If I could figure out from those 4 equations algebraically how F depends on A and divide them out, I'll get that result. Fairly strange result. Remember, the coefficients, the K's in there, all had energies, and h bar squareds over 2m, or 2m's over h bar squared, actually. All of that must have canceled, but that is the result right there once you're done manipulating those 4 equations to get the transmission coefficient. Now, you've been patient watching me set this problem up. The rest is just algebra. The physics is done. Now you have a good several pages of algebra to do to combine those 4 equations that I put boxes around to solve for F in terms of A, and then of course multiply it by its complex conjugate. And I maintain this is the answer you're going to get. Okay, I'll give 5 points of extra credit to anybody who'll take those 4 equations and prove that using the definition of the transmission coefficient, you get this equation right here. 5 extra credit points on your worksheets. Normally a worksheet's worth 4 points, so it's as if you're getting an extra 1 1/4 worksheet averaged in as a bonus. I can tell you I've taught this course now, this is the 3rd time. I've had people who've taken me up on the deal, and what the closest person who got this problem right did was to go try to Google it and see if somebody else did it in a class and finished all the algebra and posted it on some kind of class website. Unfortunately, it wasn't exactly set up the way our textbook does. And so I gave him maybe a point or 2 for effort, but didn't solve the problem. I will tell you, when you go into quantum mechanics, one of the problems that you are likely to have to do is to show this transmission equation comes from that. Okay, isn't it fun? 12:10 already, and all we've done is math. And of course, if you're ever looking for the reflection probability, once you solved for the transmission coefficient, the transmission probability, the reflection would just be 1 minus the transmission probability. One thing I want to point out when you start calculating, there is a -1 right there. Okay, so that is the reciprocal of all that stuff. That's the way it works out. This is the easiest way to do, but this is really 1 over that thing in the square brackets. Okay, so recognize that. When you start putting numbers in, sometimes it becomes a little bit tedious. All right, let's see. The next thing we got to look at. Any questions on that? You've been patient watching me do math. I'm kind of done with just a little bit more, and we want to show something. All right, remember that problem, that transmission coefficient, was for the case when the energy of the incident particle exceeded the barrier height. What if the energy doesn't exceed the barrier height? It's less than the barrier height. Well, classically, we'd expect what you see right there, that the particle would just bounce back off the barrier. But we have this wave function that we said was square root, well, whose wave number we said was the square root of 2m over h bar squared, and it was total energy minus potential energy. In this particular case, though, in region 2 here, this was K2, in this case, the energy is less than the potential energy. And so this term right here is negative, and it makes K2 an imaginary number. Well, the solution for the wave function in 2 is still, and I guess I was using E as my just dummy constant. It could be C or D, but I'll go back to using that E, just some constant times an exponent of minus kx, and that's K2, but with an I, but in this case, K2 is complex as well. So it's like you've got E times E to the minus I. K2 is complex, so you can bring out the I and just invert the order here. Turn it into V0 minus E to make it positive, and I've already factored out the I. We call it kappa once you've done that, when you invert the order. See, now it's V0 minus E instead of E minus V0, still with an X. And then, of course, minus I times I is just plus 1. And so our solution becomes, in region 2, a constant, e to the plus kappa x. And then another solution, which you can show also works, is e to the minus kappa x. And we give the coefficient d, just like we did in the case where the energy of the particle is greater than the barrier, and that becomes the solution in the middle region. Go through the same boundary condition argument that I made. You go through the same algebra, and you get a transmission coefficient in this case that looks exactly the same with one difference. It switches from a sine squared here in the transmission coefficient when the energy is greater than the barrier to a hyperbolic sine squared when the energy is less than the barrier. And just a quick thing on hyperbolic sines. We've said that e to the ix is equal to cosine of x plus I sine of x. The related identity for hyperbolic sines and hyperbolic cosines is that e to the x is equal to the hyperbolic cosine of x plus the hyperbolic sine of x. And I referred to the first one as Euler's identity, which is why if a solution e to the ikx is a solution, so would be a cosine or a sine. Well, the second one is how you relate just exponentials that don't have a complex exponent are related to the hyperbolic cosine and hyperbolic sine trig functions. And because this guy right here and that guy right there have real exponents, it flops from a cosine to a hyperbolic cosine and a sine to a hyperbolic sine. And when you work all the math through, you're left with hyperbolic sine right there. The interesting thing, though, is it's not zero. That's the most bizarre physics aspect. You would expect classically, in the case where the total energy of the particle is less than the barrier, that the transmission coefficient should be zero. And yet this thing that you work through with that math that I kind of outlined a little bit, I set it up, but I didn't do any of the algebra. You would expect classically that to be zero. In fact, this might be a small probability. It might be a very, 0.000001% perhaps is the probability, but it is not equal to zero. There's a real probability that a particle whose energy is less than a barrier is nonetheless able to get through the barrier. And that's the result of this mathematical discussion. Here's a picture of what it looks like. Okay. And so over here, you can see I've just got a wave coming in, and it is e to the I kx, and you're in region 1 there, so I should subscript that the 1. It's just sinusoidal or cosinusoidal because of Euler's identity. In right here, this would be region 2. You can see that it is exponentially decaying. The wave function looks real, but with an exponential decay. But when it gets to the other side of the barrier at x equal to L, there is still enough amplitude to the wave function that you have wave function left over here, psi 3. Okay, non-zero probability of getting through. And you could make an argument based on the uncertainty principle that the particle could have some uncertainty in x based on how well you know the momentum, and that uncertainty in x could actually extend to a distance greater than the barrier, depending on how well you knew the velocity of the particle coming in. Okay, because the better you knew the velocity, the better you knew the momentum, well, the greater the uncertainty in the position. And so it's possible that the uncertainty in position right there could extend to the other side of the barrier and allow the particle to be through. Kind of a bizarre idea, but we refer to that as tunneling, quantum mechanical tunneling, and it actually has some basis in things you may have seen in even introductory physics courses or high school physics courses. The analogy to just waves, light, is total internal reflection. If you bring in light at a proper angle, and a big enough angle, so that no light can be transmitted according to Snell's law, if you were to try to calculate for this incident angle or refracted angle for particular indices of refraction, it might be that the transmitted angle wouldn't exist, and we call that total internal reflection, in which case all that can happen is that the wave can bounce back off of that side of the prism. Scientists have found if they bring a second prism here nearby to that surface where the total internal reflection is, creating a barrier right here, right? Creating a barrier right there, that if they get close enough, the probability that the particle or the wave could be in that barrier is great enough that if you bring a second piece of glass nearby, you can catch some of the wave and allow it to come through. Okay, we refer to that as an evanescent wave. I think I'm saying that right, evanescent. And you can capture some of that probability that the wave is beyond the boundary with a second prism and actually measure light with a detector coming through. So that's the first kind of classical example that scientists knew in the day. Okay, I don't necessarily want to talk about that. I do want to talk about alpha particle decay. This could be the potential of the nucleus of an atom, and you can see the nuclear particles, the protons and the neutrons would all be stuck right here, okay, inside this well. And this function right here, that's a Coulomb potential and a nuclear force potential, which we often model, oddly enough, as a square wave, okay, a square potential. You got all these things in the nucleus of the atom. Periodically, for some heavier atoms, an alpha particle, 2 of the protons, 2 of the neutrons, get out of the well. There's an alpha particle escaping. How does it do it? How does it happen? Well, the answer is quantum mechanical tunneling. We believe that even though there's a barrier and the particles, the alpha particle, the 2 protons, the 2 neutrons together, don't have enough energy to get out of the well. It's not like we heated up the nucleus in order to cause this alpha particle to come through. Radioactive decay of alpha particles is about particles being able to tunnel through their barrier and be seen on the other side. Okay. Last thing, if I can get the right, is that. Now, here is the actual last thing. I have a movie clip to show you. So I'm going to stop sharing this and start sharing a movie, Men Who Stare at Goats. I don't know if you've ever seen the movie. Watch this. It's about Army intelligence in the Middle East. These guys actually thought they had supernatural powers. He's going into the next office on the other side of the wall, the other side of the barrier. Darn, he didn't tunnel through, did he? All right. Didn't make it. Oh well. All right. Hey, that's my humor for the end here because you've been patient watching me do math. All right. So here's the deal. We're going to come back. We're about a lecture behind right now. I've completely lost a day worth of time. All right. Let's stop that. Go away. Why to go to Goodwill Hunting of all things? So we'll come back on Monday morning. I've got a worksheet that half of you will do one problem, half of you will do the other problem. Okay. And you've already done the reading for Monday because we'll start talking not about these one-dimensional problems, but we got to go to reality here. We got to go to three-dimensional problems. We don't live in a one-dimensional world. It's not even a flatland two-dimensional world. We'll look at a two-dimensional world on Monday, but we'll be moving on to three-dimensional problems, and then ultimately the hydrogen atom. We'll look at how Schrödinger's wave equation affects that. So I guess the good news is there's no homework for the weekend. There's no worksheet for the weekend, and you've already done the reading, hopefully, and took the reading quiz for Monday because it was scheduled for today. And because I'm a day behind, take the weekend off. Any questions? Yeah, I'm sure I've dumbfounded you, haven't I? It's sort of bizarre stuff, this quantum mechanics. By the way, that clip from Men Who Stare at Goats, the way I've always interpreted that is somebody who has a little knowledge of something, extrapolates it to a ridiculous conclusion, and thinks he can get through. If you want to think about it as a physicist, there's a probability that one particle in his body might be able to make it through that wall. There is a probability and get to the other side. But what's the probability that every particle in his body can do that simultaneously? And the answer is that can never happen. But as he hit the wall, it's possible one of his atoms might have zipped through. You never know. Hey, that's all I got for you. Any questions? Then I'm going to